Assuming that you've completed the assignment and read the two essays on pages 41 and 42, I want to take a few minutes and talk about these essays. Now, this first one is one that I wrote, and the second essay is one that I stole. All is Fair in Used Cars, Love, War, and Disposable Lighters and Curriculum. So, the scientific method. Let me just start by saying this. At this level, our mandate at the college and colleges throughout is to ensure, among several things, is to ensure that when you walk out of this lab-based college level course, that you have a clear understanding of what the scientific method is, and that's spelled right out. That's our marching orders. It goes to the language of science. And this is where we get into a lot of hot water, especially these days. So let me just point out a couple of things here. In the first essay, I say, the scientific method is a remarkably adaptable tool that allows us mere mortals to pursue the most profound truths. Its strength lies in both its beautifully articulated process and its flexibility. We keep the scientific method around because it works, and most importantly, it has never failed. Now, that's a pretty brash statement, but just bear with me on this. The scientific method is something that we give the lion's share of the credit to Galileo. This was his big contribution to what we now call modern science. It's to be distinguished from the earlier idea about science from the days of Aristotle, in which they had the Pythagorean approach, which is that anything in nature, anything observed in nature could be explained through careful observation and logical inference and deduction, which is a good start. And then we progressed a little bit further and we got to the idea of Occam's razor, which is the scientific application of the KISS principle. But now here, thanks to Galileo, we have this beautifully articulated protocol for how we deal with science. And to say that it has never failed, let me be clear on what we mean by that. Science itself fails all the time. Science is 99% failure, 1% success, and that's on a good day. The scientific method, on the other hand, does not fail. Why? Well, because it is self-correcting. It's built right into its mechanism. It is a flexible, dynamic process. It's how we deal with not only the successes in science, but even more importantly, with the failures in science. What we'll find as we move along is that the failures in science can oftentimes be even more instructive than the successes. At one point, we're going to talk about one of the most important failures in experimental physics ever. And because of this experiment's failure, it literally kicked down the doors to what we now know to be relativity. But just to continue on the next page, we have this essay that I stole from Dr. Art Hobson. The book was Physics Concepts and Connections. And he talks about Galileo and how he laid out the scientific method. Now, you've probably been exposed to the scientific method at some point in your public school career. And he lays out a list. Experiments, well, yeah, you've probably heard of that, no doubt. Idealizations. That might be something that's a little more obscure. How about limiting the scope of inquiry? That too is a little bit more obscure. And quantitative methods. We're going to get into these in some depth. Further down in the essay, he talks about a scientific theory is a well-confirmed framework of ideas that explain what we observe. And a little bit further, he says, it's a misconception to think that a scientific theory is mere guesswork. Now, let me cut to the chase on this one. This is something that you've probably heard over and over again. The classical example is when we get into discussions of evolution. People who have a problem with the idea of evolution will oftentimes say, well, it's only a theory. Well, this really gets into the nitty-gritties of the language of science. In science, when we say the word theory, it has a different meaning than it does in day-to-day language. Now, if over the weekend you're talking with some friends and you say, I have a theory about the past chances for the Super Bowl this year, in that context, the use of the word theory is perfectly acceptable. It's a correct word to use. But if you were to express that same idea using the language of science, you would not use the word theory. You would say, I have a hypothesis concerning the Patriots' chances for the Super Bowl this year. Well, then, where does theory come in? Well, theory in science is this large, overarching body of knowledge. Analogies are always a little bit dangerous, but if we want to keep the football analogy, could we not agree that there is an overarching theory to football? So that would be one way to look at it. We also oftentimes hear, well, if scientists are so sure about X and Y, why don't they just call it a law rather than a theory? And the answer to that one is, laws are pieces and parts of an overarching theory. We could agree that electronics is an overarching scientific theory. Contained within it are all sorts of laws. Here's an example of one of these laws. This is the first thing you learn when you learn any type of electronics. You learn something called Ohm's law. Ohm's law, it says that energy, voltage, is equal to the current times the resistance in a given circuit. So energy equals current times resistance. Now that's just one little tiny law within this overarching body of electronics theory that makes it the theory that it is. But it sure as hell isn't the whole thing. You could, that's just the start. So this is important. This is the important takeaway. Laws within a theory are little pieces and parts of the overarching body of knowledge. The other thing to consider about what constitutes a theory, I'm going to spend some time with this, is to understand that for a theory to be a valid scientific theory, it has to contain within it its own suicide switch. It has to contain within it a means of being tested up to and including the point of being disproven. If you can't test it, then it's not yet a theory. That's the other part that's very, very important. It has to be something that is testable. This is what Newton was all about, repeatable, testable results. So that's the other piece that has to be in a valid scientific theory. It has to be testable. Now, on the next page, we'll go ahead and break this down. On the next page, on page 44, you see a scientific method flowchart. Now, I stole that one too. I found that in a high school chemistry book. It was the best layout of the scientific method that I've ever seen. And so, again, I stole it. All is fair. And before we even start scribbling in this, I'd like you to just take note of the arrows on either side, how it works as a flow chart. It goes back and forth and back and forth. My kid sister, who is also a science teacher, she refers to such things as trying to nail Jell-O to a tree. And it's kind of like that. But you see how it's dynamic, how it's adaptive. It's a flow chart. It's not rigid. It is not rigid. Too often times, the scientific method is presented to students as this very rigid protocol, and it's not. It wouldn't work if it was rigid. It has to be flexible. It has to be self-correcting. So let's look at some of the pieces and parts here. The first thing we see is observing. Now, under observing, there are 4 items for your consideration. Number 1 would be collecting data. Number 2, measuring. Number 3, experimenting. Number 4, communicating. Right. In other words, this is where you're just starting, you're getting started here. So there they are. Under this overall idea of observing, we have collecting data, measuring, experimenting, and communicating. The next block. Under generalizing. All right, you've collected your data, you've done your measurements. Now it's time to see what you got. Number 1, organizing data. Two, analyzing data. 3, experimenting. 4. Yep. I misspoke here. Number 3 is classifying. Okay, number 4 is hypothesizing. Number 5, inferring. Number 6, predicting. And number 7, communicating. All right. Okay, organizing data, analyzing data, classifying. Okay, organizing data. Well, I got a bunch of birds, I'm going to put them in a pen. Analyzing data. Some of them got webbed feet, some of them go cluck. Classifying. Well, those are ducks and those are chickens. Okay, hypothesizing. All right. Yeah, I guess they're two different kinds of birds. Inferring. Remember, if I imply something, you infer its meaning. Predicting. Well, I predict them go quack and them go cluck. And communicating. Hey, look over here. I got a bunch of ducks and chickens. Communicating. All right. So there it is under generalizing. It really isn't that much more fancy than that. Under theorizing, constructing models. Number 2, predicting. And if you predict that the third one is communication, you would be correct. You would be correct. Okay, so that's under theorizing. Finally, the last block, testing. Number 1, predicting. And number 2, you guessed it, communicating. All right. And there at the bottom of the page, communication is common to all steps in the scientific method. Communication is key. If you don't communicate, then it ain't no science. So remember, science is what humans do. What are humans doing? They are trying to understand X, Y, and Z. And to do that, they must communicate these ideas. So communication is the critical piece to every aspect of the scientific method. All right. Now, the next page, page 45, I think it is, 44. Page 44, we'll look at the nitty-gritties of these different ideas. So, let's take a look at this idea of a theory. Okay, so what is a theory? Well, a theory is a body of knowledge that is supported by laws, mathematical and physical evidence, and repeatable, testable predictions and or results. There, did you get all that? I'll write it down for you. Okay, there it is. A body of knowledge that is supported by laws, mathematical and physical evidence, and repeatable, testable predictions and results. All right, so by the time, what we're saying is by the time something reaches that level of being called a scientific theory, it has been tested and tested and tested and tested and tested. Now, sometimes certain features of a theory will fail a test, and we need to be very careful about this one. In broad terms, what Newton had to say about gravity, Newton's theory of gravity, is, for the most part, pretty correct. But there were some features of it that were not correct, that we did not know until a fellow by the name of Albert Einstein came along and showed that there were certain aspects of Newton's ideas, Newton's theory of gravity, that were incorrect. Now, did we throw the whole thing out? No, we did not. We still use Newton's laws to this day. Newton's laws are what got us to the moon and back. And so in science, we don't when something comes up that will show a feature of a theory to be incorrect, we don't throw the baby out with the bathwater. Instead, what we do is we modify the theory. Now you might be thinking about, well, what about Ptolemy's model of the universe compared to what Galileo was able to demonstrate with his observations? Well, that is by far more the exception than the norm, because what Galileo discovered and verified through tangible evidence was something that was fundamental to Ptolemy's theory. And so the very foundation of Ptolemy's theory was disproven in this case. All right, so, but that is by far more the exception than the rule, especially nowadays in the 21st century. This is where we tend to modify theories rather than to throw them out entirely. It does still happen. It does still happen. There was an idea up until the early 60s of something called the steady state universe. And it competed with something called the Big Bang theory. And eventually the steady state theory was disproven, but certain features of that steady state theory were correct, and we still use them today. But anyway, that's the general outline of what a theory is. Now, compare that to a hypothesis. What is a hypothesis? Number two. In brief terms, it's an untested idea. And I'm going to give you one other definition for a hypothesis. A swag. What's a swag? That is a scientific wild-ass guess. Now, in my time in the Navy, I spent a lot of that time as an intelligence analyst. And the protocols for that analysis were almost identical to that of the scientific method. It worked in a very similar fashion. And sometimes in science and sometimes in intelligence, that's all you got is a swag. And so every now and again, you might just have to pull out a swag and see what happens. So that's fair game. The next one is idealizations. This one's a bit long-winded. That's courtesy of Galileo. It's elimination or discounting of insufficient or irrelevant data and or conditions in a given problem, scenario, or experiment. Here we go. So there it is. Elimination or discounting of insignificant or irrelevant data and or conditions in a given problem, scenario, or experiment. An example of that would be if I was going to talk about the time it would take the laboratory rock to drop from a certain height. Now, did that rock encounter air resistance? Yes, it did. Enough to count toward the experiment? No. So I'm not going to get bogged down with that. Okay, this is Galileo. Quite frankly, this is Galileo telling us, don't get bogged down in bullshit. Really. How many times have you been in an argument with somebody and they keep trying to bog you down in BS that has nothing to do with the topic at hand? Well, that's Galileo telling us, don't do that. Right? And he was pretty smart. Okay, limiting the scope of inquiry. That also comes from Galileo. It's breaking a complex problem into individual pieces. And I'm going to give you one more. I'm going to give you one more definition for that. The pizza principle. Look. You call up Domino's, ding dong, the guy shows up. There's Freddie Pimpleface there with your pizza. You give him his money, you take it inside. Now, you choke down the whole pizza all at once? Oh, well, yeah, I did once. I won $50. Aside from that, what do you do with that pizza? Well, you slice it and you bite it, all right? The Navy SEALs have an unofficial motto. How do you eat an elephant? One bite at a time. This is Galileo telling us this is how you should do complicated problems. The perennial bugaboo for a lot of students is word problems. Don't you hate word problems? You look at a word problem, you go, oh my God, how the hell am I going to do all of that? And the answer is, you don't. You don't. You do one little piece at a time. Understand this about mathematics in particular. Did you know that the human brain can do one and only one mathematical operation at a time? That's it. That's the limitation of the human brain. So don't fight that. Acknowledge it and work with it. This is how you survive physics problems. Doing a piece at a time. The pizza principle. Okay. Quantitative methods, also from Galileo. This one's easy. Numbers, numbers, numbers. This is it. This is it. Now, how is that relevant? Well, let's look at the difference between what Aristotle would say and what Galileo would say. Galileo would say that this rock is heavier than this marker. And he would be correct. But that is not a quantitative assessment. That is a qualitative assessment. And that's not good enough for science. In science, you got to have numbers or you ain't got diddly. All right? Galileo would say this rock has a mass of 375 grams. This marker has a mass of 85 grams. Okay, that's numbers. I can work with that. Numbers are critical. Okay? No numbers, no science. It's that simple. Number 6, creating a model. It may be an actual model. It can be a sketch. Or it can be a mathematical description. So yeah, it can be an actual model. Aeronautical engineers, for instance, will come up with a new aircraft design. One of the first things that they'll do is they will create a smaller scale model of that aircraft and put it in a wind tunnel just to see how it behaves. So yeah, an actual model. A sketch. Listen, the way to survive physics is to draw pictures. And if you can't draw a straight line, then invest 75 cents and get yourself a straight edge. All right? Start drawing pictures. And we'll get into that when we start getting into vectors, especially. That's going to be very critical. Get used to the idea of sketching things. Now, we're not going to turn this into Maine College of Art. That's not the idea. But yeah, do get used to the idea of sketching things out. Galileo did it. It's good enough for Galileo. It's good enough for us. And a mathematical description. That too can be a model. If you watch the weather, you'll hear them talk about what computer models are indicating for a hurricane. Well, there's an example of a mathematical description or a model. Okay, so yeah, that's what we mean by modeling. Okay. Number 7, repeatable, predictable results and outcomes. Number 7, all right, this one's real easy. That is the deal breaker in science. Repeatable, predictable results and outcomes. Yeah, you've got to be, if for you to have a valid scientific theory, it has to contain with it means of making predictions. And those predictions have to be consistent with the model. Okay. Finally, fact-based rather than than authority-based knowledge. Okay, fact-based, we've kind of been dancing around this a bit, so let me just say this. Fact goes this way. Tangible evidence. To include observations, to include mathematical models, to include an idea supported by laws and so forth. In other words, a true scientific theory. What's authority-based? A good example is this one. Invoking invoking deity is authority-based knowledge because the church says so. And again, this is not about church bashing. This is just about understanding which is what, where the line in the sand is. Overall, this idea of a scientific method, it's a way of thinking. And this kind of goes to what Einstein had to say about what college is about. College is not about loading you up with a cache of facts. College is about teaching you how to think. That's the deal. And the scientific method is a way of thinking more effectively. Now, this is not to suggest that anybody here taking this class doesn't know how to think. Of course you do. You know, you all made it to college. That means you can hit the floor with your hat 3 times out of 4. Okay, got it. But it's kind of like this. Let's say, all right, everybody here knows how to walk. Now we're going to teach you how to dance. That's kind of what we're saying here in terms of what the scientific method is. It is a way of thinking. Whether you go into science after the end of this course or not, you know what? It's still a pretty handy tool to have in your back pocket. It's a way to think more clearly. It's a way to wade through the BS that's out there. And as we all know, it takes only 2 minutes on social media to see how much BS is out there. We want you to be able to think clearly. All right, so there it is, the scientific method.